7 or 8 people down in the room itself, and I can see at least 5 people online. So welcome everybody. Tonight we're very lucky to have Roger Harrison presenting to us, and I think we'll move straight on to his presentation. Roger, VK2ZRH, he's going to talk to us about Sporadic E, its origins, its haunts, and its habits. For those that don't know Roger, it's his birthday today, incidentally, so you can join with me in congratulating him. He's a fully accredited expert in this field of Sporadic E, one of the few in Australia who really knows what he's talking about with Sporadic E. And so we'll keep the formal bits of the meeting to the end. There's a little bit to talk about, but I'll hand you over to Roger now and look forward to what he's got to say. What I'll do what I'll ask is the same as I always ask, because we're recording this to go up on the website, is that we'll keep all the questions to the end of the session, if that's okay. And it just makes the editing a little bit easier, and then we can hear all the questions, because we've muted the speakers in the room now, so until the presentation's actually over, we won't be able to hear you. So we'll just hold all the questions till the end. Okay, I'll hand over to Roger. So if you want to start sharing again, the floor is yours.
Okay, let's see what we can. This is a bit slow in trying to share.
Okay, so we're there, everybody. Sorry about that. Right.
Yes.
Thank you, Andre.
Thanks very much.
Thank you. Okay, here we go.
But sorry, final check. John Morris, can you just thumbs up that you can hear us? Lovely, thanks.
Excellent. Thank you very much. Okay. Ever since I was knee-high to a grasshopper, I've been interested in propagation. Right from before I got my license, it was back in 1963. I decided my interest lay in VHF because I'd spent 4 or 5 years as a shortwave listener, and I decided to move my sights upwards. So I organised to get myself on 6 metres when I was a student in Melbourne. And so I ran into Sporadic E. That was the big deal VHF at the DX at the time. So it was fun. So the following presentation is non-fictional and definitely depicts actual situations and events. You are warned that images and diagrams may depict DX that has been missed. Our experience of ES propagation can be quite capricious, but exciting. You come to expect the unexpected, stops and starts seemingly without warning. Signal strengths range from rock crushing to wisping. Unknowing ops blame foundation calls for high power. Our experience of VHF ES propagation, when the band's open, it's often chaotic. Propagation may jump from area to area. Stations a few kilometres away work others you can't hear. The MUF might rise over hours or only minutes. Signals can appear and disappear suddenly. They last only minutes or for hours on end. They're often strong, punctuated by deep, rapid fades. Sometimes appear from unexpected directions. Every sporadic E propagation event is different. Now, what happened in the morning and what happened in the afternoon are 2 different events. How curious. So, here's where I began. That was my shack at 1 Mary Street, North Balwyn. You can see the multimeter in the panel at the top left. Not a multimeter, true multimeter, you know, with multiple meters. That receiver there was a stripped down ex-Defence 3BZ, totally rebuilt, suit my specifications. these days. Of course, I was spending more time on the bench, accumulating papers on Sporadic E. So that's the pile that it's got to in the last couple of years, all of those folders. So let's have a recap of the ionosphere. In the night time, you've got an E region and an F region. In the day, that becomes a D region, E region, F1 and F2. You might remember this from when you studied for your license. In each of the regions, we have gaseous ions, nitrogen, oxygen, and nitric oxide. You get different densities at different heights, electron densities and temperatures. So as you see, as you rise, you get into the thermosphere, which is where we play. And sitting in the thermosphere, we have the ionosphere, of course, electron densities varying up to 10 to the 6th per cubic centimetre. That's a million. That's only partially, actually weakly ionised. It would be much greater than that if it were fully ionised. That rarely happens. So let's take a look at how the atmosphere is broken up. In the lower part, we have the troposphere. And there's a height at around 10 kilometres or so where the temperature plunges dramatically. It's called the tropopause. It's a pause because the temperature rises after that until you get the stratopause in the stratosphere. Curious, they put very obvious names on this. It saves all of the explanations. So the temperature falls again until we get to the mesopause. And it rises again right through in the thermosphere. Sporadic E, for our propagation purposes, sits in that region just there, you see on the top left. At mid-latitude, Australia, New Zealand, North America and Europe, sporadic E are thin, dense clouds of metallic ions, not gaseous ions, and free electrons. The ions attract the free electrons. So from the layers are from under 1 kilometre to maybe 5 kilometres thick, lying at heights ranging between 95 to 150 kilometres. They comprise maybe one or more clouds or patches. That could be continent sized, but you know, thousands of square kilometres or maybe only 100 metres diameter. So if we look at sporadic E patches as recorded from the Jindalee over the horizon radar, this is the sort of thing you get. If we look straight up at the electron densities, you get this very sudden, very dramatic peak. And it often exceeds the electron densities present in the F region. So how does it happen? Well, it's called, let me explain this. It looks a very complicated diagram. You see all that row of pluses there. Ions are pushed into a thin layer by the action of winds and the magnetic field. So a westward wind sitting above an eastward wind, the westward wind pushes the metallic ions downwards, whereas an eastward wind pushes them upwards. So hence you get them bunched into this thin layer. And the electrons move along the field lines to follow the ions. And it's the electrons which do the reflection for our signals. So the wind shear theory, which was first enunciated by Professor David Whitehead from University of Queensland, So he spent all his working life up here. Quite a nice fellow. I met him on a number of occasions. It's, he managed to put this in an equation. So if you look at the top part above the line, you see the HI. That H is very important because that's the representation of the geomagnetic field. It typically takes 100 seconds to compress the ionisation once you get a wind shear. If the process was perfectly efficient, says Dr. Whitehead, Sporadic E would only be 100 metres thick. But like people, nothing's perfect. So, things to note. Left to itself, Sporadic E layer or cloud would disappear in a few minutes as the ionisation would disperse by diffusion, just as it does with meteor scatter. That's why meteor scatter contacts are brief. The clouds are the ionisation trail behind the meteor plunging through the ionosphere is blown away by diffusion. The wind shear ensures continuous formation of sporadic E, even if there are large changes in the horizontal winds. Wind shear occurs both day and night. Interesting. So sporadic E occurs daytime and nighttime. Some people think it's a daytime event only. Not so. It's not strictly produced by the sun. So it's a stranger in the ionosphere. Two or more thin layers can form a stack separated by perhaps 2 to 10 kilometres. So here's an example taken with rocket looking at measuring the electron density with height. And you can see very clearly that there's 2 layers there stacked. So the life cycle of ions is very, very important to the formation of sporadic E. The metallic ions that are present in sporadic E are iron, calcium and magnesium, mostly iron and magnesium. So it starts with meteor ablation down there on the right-hand side. And the ions produced there, it's scattered and weak, but atmospheric processes push the ions upwards, they drift upwards. And you get photoionization from the sun, and you get charge exchange with what's happening with the other ionization in the ionosphere there. Eventually the ions descend through gravity and diffuse down the field lines. So you get descending sporadic E layers there forming with wind shears on the left-hand side. So they converge in that small space. So the life cycle, this is very interesting. It's greater at altitudes, at higher altitudes than lower altitudes. So they will last, the ion will last for days at heights of 100 kilometres and above. So what's happening here? Towards the equator, you get forces in the electric field in the ionosphere and the atmosphere, which will drive the ions, those stray ions, metallic ions, up through the atmosphere, and they drift down the magnetic field lines, and they end up in the mid-latitude regions. So we're mid-latitude. Here it is. This is a not really a fanciful representation, but it generally explains it. and it's curved like that because of the shape of the Earth's magnetic field. The part between 10 degrees north and 10 degrees south, the field is flat pretty much, so it doesn't form like that. You don't get sporadic E forming like that. You do get sporadic E in that region, but that's a discussion for another time. So how's it all going? You've got to line up a lot of ducks in a row just to get wind shear occurring. So on the left there we see representation of the Earth and the ionosphere of the atmosphere. Solar radiation heats the Earth on the side facing the sun. It heats the atmosphere and the thermosphere. But you get winds moving in that direction and moving away from it. So the thermal tide, the expansion and contraction of the atmosphere, right down to the troposphere, right up to the thermosphere, it has this diurnal variation, as you would expect. So solar radiation drives the global thermal tide. And thermospheric winds from polar cap processes excite planetary waves. These are waves, large scale, quarter wave around the planet. They come with periods of between 2 and 16 days, typically 2, 5, 10, 16, like that. Hey, what's happened here? It's decided to...
Let's see what happened.
I tried to switch to the next. There we are. Right. So, now gravity, or gravity waves, are more like buoyancy waves. When you throw a beach ball in the water, it initially sinks and then bounces back up again, maybe a couple of times. But in the atmosphere is a soup of waves and bubbles. They rise and move and etc. So gravity waves affecting the lower thermosphere, around 100 kilometres, arise from shocks and ripples in the lower atmosphere and in the same region. So planetary waves are sort of like form large vortices in the U region, neutral atmosphere. And we get a wind shear because of those circulating vortices. The atmospheric tides, planetary waves and gravity waves combine to generate wind shears that create sporadic E. So you've got at least half a dozen, ducks to line up in a row just to get there. I wonder what happens. Now those planetary waves, seasonal waves, have these seasonal effects. So as you can see, it's different in the northern hemisphere to the southern hemisphere. It's generally thought to be because of the tilt of the Earth. So in the northern hemisphere, if you look at the occurrence of mid-latitude sporadic E, and you look at the winds, the planetary waves, etc., they line up. North-south planetary waves and east-west. So hence you get this effect, seasonal effect. So if you map out a season, here we are across 2 years, and you look at local time on the left and right hand side there, and then the percentage of time that sporadic E penetration from an ionoson looking vertically is greater than 5 megs. Now that's the definition of strong or intense sporadic E. in terms of ionospheric research. So I'm going to get a couple of occasions where it's greater than 90%. But look at the left-hand group and the right-hand group. They're different, quite different from one summer to the next. And of course, summer's in the winter there. So this is a northern hemisphere, mid-latitude, Washington, DC. 49 degrees north geomagnetic latitude. Now, I had a go at looking for planetary waves in Sporadic E from the Canberra, no, the Sydney ionosonde back in 2009. So for every half hour, I mapped whether Sporadic E above a certain frequency was present. So that for all of those half hours, around 39,000 of them for the December, for the month, you can see the peaks. And I've picked out the various ones. You can just see by visual inspection the planetary waves, the effect, the likely effect from planetary waves there. So you numbers there, 2 days, bringing it on, 5 days, 10 days, 16 days. So if we look at diurnal variation across a year, local time, etc. This is the Brisbane ionosonde, the intense Sporadic E. In the middle is summer, and the winter months, June and July, are at the ends. And the local time is 0 at the lower point and 24 hours at upper right. Here we are for Norfolk Island and for Canberra. Now there are similarities, but very considerable differences. If I had one there for Brisbane next to Canberra, it would look quite different as well. Now it's the atmospheric winds in the lower thermosphere at 100 kilometres and around that is driving this diurnal variation. It's not the solar radiation. So, Sporadic E in the solar cycle. Now, on the left-hand side, we have a percentage of Sporadic E, of strong Sporadic E, contours there on the left and right. And it's different at high solar activity and low solar activity. But if you look at two propagation paths of typically 1,500 kilometres, the propagation will be different. It's opposite, the high versus low solar activity. So there's a disconnect. Okay, Sporadic E on ionograms. The Space Weather Services, as previously known as the Ionospheric Prediction Service, or IPS Radio and Space Services for a time. I worked for them for 7 odd years back over the 70s. I learned a lot. I was taught a lot as well. So we have an antenna system which points straight up. We have a transmitter system which creates a pulse, and it's turned around by the ionosphere and it's received back at the ionosonde. Sounds fairly straightforward, and this is the sort of thing you get. So on the left there, right at the lower left, you get an E layer. Fortunately, this is Brisbane, so it's all local. And the annotation is what is used throughout the world in ionospheric science. Now, the difference between the ordinary O and the extraordinary X reflections there in the F region and in the E region is brought about by the fact that we have a magnetic field. So they're retarded differently. The electrons in reflecting the radio wave impinging upon them, they slow down and return differently. So for the ordinary reflection there, the electrons are trying to go across the magnetic field, whereas for the extraordinary, they're sliding up and down the magnetic field lines. So we'll come across these terms as we go along a bit. So an ionosonde antenna's view, if it is pretty much a triangle like this, isosceles triangle, with the antenna beam width at the lower frequencies is typically 90 degrees, and at the upper frequencies are typically 60 degrees, even with the peculiar antenna systems there, the more progressive antenna systems they're using these days. Now that's important, as we'll soon see, because not everything comes from directly overhead. So here's a sporadic E layer. It's plain because it's flat, and it's blanketing. You can't see through it to the F region. Here's a passing gravity wave, a passing atmospheric bubble causing a transient wind shear. On the left, you sort of vaguely see some weak sporadic E. 5 minutes later, bang, you've got this sporadic E layer. It's flat, it's strong, and the top frequency is 13 odd megs. That would definitely support 50 meg propagation, even better. 5 minutes later, it's kind of decayed, and the weak sporadic E is still weak. So let's talk about propagation, the propagation geometry. This is traditional ways of delineating propagation paths and the characteristics. These days, of course, they look at working it out different ways, but there are, with computer power we have now that wasn't available previously, but the results, shall we say, are pretty congruent. So it all depends on the angles. The maximum usable frequency, the NUF, depends on that angle there, B, with the rate between the ray path and the sporadic E. Now there's a multiplication factor called the M factor, surprise, surprise, which leads to your MUF. So if the penetration frequency, the top frequency where you don't get a reflection on sporadic E anymore, it's known as FOES there. You divide it by the sine of that angle and you get an MUF factor, an MUF, sorry. Now if you plot it out, this is the sort of thing you get. So at different heights, different M factors, ray path elevations, etc. So, and of course, the lower the ray path elevation, the greater the MUF factor. We'll come to that again shortly. So, now here's a different ionogram. Look at it, it's all hazy and spread and fat. And there's a strange second one in the middle there. Now that's not necessarily above In fact, it's guaranteed not to be above. It'll be off to the side somewhere, hence the greater delay. Now, this sort of sporadic E event would certainly support 6 metre propagation, almost 2 metre propagation, and there's a reason for that. So here's where we can see through, or non-blanketing spread ES. So we can see the F region and the reflections between the ground and the different layers. So F2 plus ES, etc., twice F2, and various versions of it. And there, an example of twice ES of vertical. That would definitely support 6 metre propagation as well. So, propagation via spread ES is different. It's spread because it has ripples or boulders or lumps, etc. They're only comparatively small, sort of like kilometres, hundreds of metres to kilometres long between ripple peaks. Sometimes there's, it looks like those puffy clouds that break up, and you can see the blue sky behind them. Now, what happens here is, of course, this is an example of caudal hop propagation, but it's not very large distance, as we get in some other regions of propagation. So I've called it petty caudal hop, just to add a bit of culture French in there. So spread ES multiplies the MUF considerably. There's that M factor diagram from plain sporadic E. And you can see it pretty much doubles the MUF factor. And sometimes you get, I've called this a surprise sporadic E. This is spread, of course. And the second reflection indicates that the top frequency is much higher than it appears to be at the first reflection. Now, it appears like that because it's spread, that will support 6 metre propagation where otherwise it would not. It would support 10 metre propagation. So why do we get really strong signals? Well, you get ray path focusing. So it has a density, and of course the different angles of arrival can produce a convergence on the ground. So how big does the convergent area get, or how small does it get? Well, I have a documented example where I once drove through a spot on the ground and estimating the speed of the car and the time the signal was present. So it's about 3 kilometres. That's why somebody a few kilometres away from you can't hear the signal, whereas the other person's going, no, it's 5 to 9. There's a good reason why it's 5 to 9. It's focusing. This is very common, much more common than widely believed. Same thing happens with spread ES because of the way the ray path travels through the ripples. You get convergence on the other side because of divergence on the incoming. So around the Earth, remember that, see the equation on the top right there, that H, which is the strength of the magnetic field. Now this is a plot of contours of the strength of the geomagnetic field. And it's very high over Southeast Asia, you see, and rather weak over the South Atlantic, which explains why trying to work South Africans from Australia has not been done yet. I just say yet. Now, we have 4 places there which are important. So if you look at the recorded ionospheric behaviour over time, from the left, B, Fort Belvoir, which is USA, W, Wakamai in southern Japan, and Kokabunji in central Japan, and Christchurch in New Zealand down there in the south. So here we go. So if you look over the year, of course, the summer months, you get much higher periods where there's strong sporadic E. This is really strong sporadic E, if it's greater than 10 megs in the FOES. And of course, Christchurch being in the south is the peaks are away from the ones in the north. Now, here's an expression of that. This is taken from, this is mapped from satellite occultation of UHF signals, actually 1500 meg signals from the satellite group that are constantly circulating. So you see, this is summertime. You see that the whole over the South Atlantic, and you see the really strong occurrence rates over Australia and of course the Pacific. And this whole, which is snakes across the equator. Now, if we look at the Northern Hemisphere summer, you get the inverted picture. It's very strong across Europe and the North Atlantic and the North Pacific. You see below the geomagnetic equator, there's some weak occurrence rates. So that's the midwinter maximum we get, and for opposing the Northern Hemisphere summer maximum of occurrence. So, multi-hop sporadic E propagation. If they're getting clouds here and there, and it doesn't spread right across the globe, how can we get multi-hop? I mean, it's counterintuitive. If you think about it, you know, you've got to think, well, there's got to be an occurrence here and an occurrence there. Do they all line up? Well, they do. And there's been a lot of work done on it in the last decade or so, decade and a half. Now, this is a map of VK3OER's chirp radar and the results. And here we get the reflections. And you can see, you know, what is it there? First hop, second hop, etc. All those peaks going there. But the intriguing thing about this, since this was done, is the peaks and troughs that look like noise between the obvious peaks of sporadic E propagation. That suggests, in fact, that there is small puffs, some weak sporadic E, and so digital nodes will be able to take advantage of that. It's probably what's happening. Now, here's a multi-hop example that I traced, and was confirmed by the operators at each end, Jack OA4TT and Mike VK2FLR, both silent keys, unfortunately now. So 1, 2, 3, 4, 5, 6, 7, 8 hops across the Pacific. So I looked at what was happening and then at the ionosons and 3OE's chirp radar at the time, and was able to trace what happened with this path. Now, not all of the hop distances are the same because conditions with the height of the layer vary. Okay, on to the current time, 15th of January, the field day. There was a lot of sporadic E around. Doug was working VK3s and VK5s. And so I looked at the Canberra ionoson, which would give an indication of what sporadic E there was around. This is really intriguing. There's sporadic E in all directions. They're not stacked layers. That's just quite a bunch of clouds passing by. So more recently, morning of the 25th of January, just after the field day. So why are they 10 days apart? Well, we go back to those planetary waves and their cycles, 2, 5, 10, 16 days, 10 days apart. So I picked the 10th day and had a look at all the ionosons around Australia. This is Canberra, that'll support 6-metre propagation. Again, at 10:30, this was the 10:10 in the morning, 10:30 in the morning. It changes to fully blanketing. Pretty much.
Were there contacts being made?
What's that?
Were there contacts being made?
Yes. Here we are 10 minutes later. So it changes rapidly, as I outlined early in the piece. And this, the MUF starts to climb because we're getting spread ES. Here's Hobart in the morning. Learmonth in the morning. That's, Western Australia, midway up the coast. Again, that'll support 6-metre propagation out into the Indian Ocean. And Darwin, around midday. That's extraordinary, that one. So here's Canberra. The MUF on the VK4, VK3 path here would be greater than 200 megs. So what will we see in a field day of the future? Probably something like this, after Norman Lindsay, Australian artist. And next week, we've got amateur radio appear in your letterboxes or in the news agents. Thank you, folks. That's it.
Thanks, Roger. Now, so that we can hear any questions that might come in, we might switch off. You can stop screen sharing. Let's see if we can do that. No, that microphone over there should still work. Questions for Roger? I'd like to thank him first of all for a fantastic presentation. I've learned a couple of things that I didn't realise before, and I'm more confused than ever about some of the other things that I thought I understood, but that's part and parcel of the process, I'm sure. Any questions from those who are coming in online?
Yeah, I'd like to give one question. I thought that was a fantastic presentation because you've really cleared up what sporadic E means for me. But is there any, you know how you get thermals from heat from the Earth? Is there any contrast with the Earth to the sporadic E? You didn't seem to mention anything about heat, but you sort of said something.
Well, the thermal tide affects the wind shears.
Yeah.
That's just the sun heating the neutral atmosphere. You do get effects in the lower atmosphere, which translate to the ionosphere. Volcanic explosions, for example, although the dust cloud from the volcanic explosion might reach 35 or 40 kilometres, so it's gone well past the stratopause. But the shock wave will affect the ionosphere right through to the F layer. You do get other effects. For example, winds in the troposphere, which persist for a time in some regions. And I'm thinking particularly of the Middle East, Anatolia, in the Mediterranean. The mountain ranges in Turkey, you get an atmospheric planetary wave there, which blows a very strong wind, and the waves from it, the gravity waves from it, reach right through to the lower F layer. So, and that's responsible for some sporadic E in Eastern Europe and that sort of region. Similarly, I'm informed that the Pyrenees do the same sort of thing. You get waves from wind systems in the troposphere bounce right up to the lower ionosphere. They're trying to use it to predict what they do. I'm not very terribly well at it. Sometimes it works, sometimes it doesn't. There are too many ducks to line up in the row.
Fair enough. Thank you.
Can I ask a question? You showed us, Roger, the E layer ionogram.
Yes.
And showed us that obviously the higher end of the frequency that's coming back from a directly overhead cloud. Is there a magic number that you can multiply the highest frequency to what the sporadic E will get to? And we've all known that once you start seeing reflections above 8 megs, that 50 megs is starting to work. You don't see 50 megs coming back down because it's vertical incidence. I understand that. But is there a magic number that we can, as mere mortals, use to say, all right, I can see reflection coming back at 10 megs. I can expect sporadic E to extend from the out to what frequencies?
Well, it depends on the height and and of course that affects the angle propagation. So we're not talking about the angle of the maximum radiation angle of your antenna. We're talking about below that.
Yep.
Because most sporadic E propagation typical distances of 1,500 to 900 or 2,000 kilometres is in the 2 or 3 degrees.
Yep.
Now you're getting an antenna to do better, to get a maximum load there is extremely difficult, if not impossible. BOE has managed it because he has picked a hill in which there is no clutter for kilometres and it slopes away in pretty much every direction. So he can get his major load shoot
degrees. But
That's out of
suburbia,
hardboard.
what we're getting, with the 4 element yardie, never mind the 10 element yardie, the best you seem to get is typically between 7, 6 and 10 degrees. Is that peak load? So you're depending on what's happening in the running down the back of the road underneath. So the gain there, you're losing 10 dB, 15 dB, but you're still getting 5 to 9 signals.
So we usually, as a frequency, you sort of, at bottom line, just multiply that by 10, and that's usually a pretty good rule of thumb.
Well, the MUF charts I showed you there, because it actually gives you that. So it depends on height. So it depends on the height of the layer. Is it at 95 or is it 105 millimeters? So that will vary the angle of incidence. And that the lower the angle of incidence, the higher the MUF. So for a plain ES layer, no rippling, no spread ES on the ionogram. So that figure is maximum of about 6. So you multiply the top frequency, or you subtract, half a meg actually, for this reason, 700 kcs from the top frequency, and then multiply that by the MUF factor. And that will give you, and that's typically 5 or 6. Okay. Between 5 and 6. That gives you a rule of thumb. If you know what the height is, if it's 90 kilometres or 95 kilometres, will be due. You can use a higher number.
Okay.
More closer to 6 than 5. If it's at 110 or 120, then you're down around the region of 5. But that will, so if you see an ionogram in which it's about between 8 and 9, in the top frequency, you'll get 6 metre expect 6 metre propagation. But only if you're looking at the Canberra ion song. Don't look at the Brisbane ion song, it'll tell you nothing about your propagation.
Yeah, we always look for the community.
Roger, could I raise the long sought after possibility that radio amateurs have had of having a sporadic E contact on 432? I remember, perhaps with digital modulation techniques, it could have been done somewhere, but I've not heard of it. But I do recall during a very intense 2 metre propagation thing, I was in Brisbane, and Doug, the late great Doug, VK3UM, was somewhere where he was. I think still at Chermside in Melbourne at that stage. But he was using his 432 array, which was very focused, and there was no one to talk to on 432, but he was actually mapping by moving his antenna around, actually picking up background noise, and he could get the shape of this sporadic E cloud on 432. So what he was, there are a number of I've spoken to the individuals involved, a number of one-way reports. Mm-hmm. One person also claimed a contact, but has not kept the documentation. So you can only regard it in scientific terms as suspect. I believe the guy, but I've seen TV signals in the high band received via sporadic E. But to get that sort of MUF, it's got to be pretty much spread ES. It's got to be rippled.
The question about the rippled stuff when you get the multi-box validation, that's for transits of contacts. So must experience one of those in Hawaii a couple of weeks ago.
Probably.
So that's over the water, generally. The sea's been used as one of the
Well, yeah, one of the reflections like that, GK2FLR to LA422.
yeah, so if I'm thinking about when we want antennas to Europe, doing 6-meter contacts to Europe, you get enough reflection off the land.
Yes. Yes,
So it doesn't absorb.
Brian 5BC has done that, and of course the indefatigable 3OT. In order to get into Europe, he's got to get at least 2 ops across Australia.
That's better.
Kevin and I have just been receiving whisper signals of 40 megs from the state.
Yeah.
Which would be the same rate of propagation.
Well, when it crosses the equator, there are 3 ways that will cross the equator. Firstly, it's got to get across the that centre zone around the geomagnetic equator. And you get sporadic E, which will support 6 meters in that zone. Even though the field, the magnetic field is flat and would not support the compression of the ions, metallic ions. But fortunately, what happens is you get an effect where there's an electric field sets up between the E region and the F region, only during daytime, daytime only, and it will support propagation up to 70 megs or so.
We were getting these overnight. It was weird.
Right. Well, yeah, the other way of crossing the equator is via the F region with transequatorial propagation. Or you're just getting E-hop. Yes.
Yeah. we could see it pick up for about an hour or so in the morning, then it disappeared. But overnight you should get it sporadically.
But what they're reporting is probably using a whole lot of those little blips and pops and things that on the decaying graphs that you show.
Yes, yeah, that's right. So because what that represents is scatter in the ionosphere where it's rough, and so you get pretty localized concentration sufficient to cause refraction, sufficient refraction, so you get a reflection again. The size of them would be smaller than this room, so
More ducks to line up.
Oh, more ducks to line up. I did notice a curious one some time ago. I wrote it up in AR. Brian 5BC worked Sicily. There's a guy up there in a village called Gibble Manor. We confirmed the contact. I had an email with him, etc. And it was afternoon. It was morning it was late morning in the Mediterranean, and afternoon here, of course. And exactly the same contact happened exactly 10 years later, to the day.
10 years.
Yeah. Extraordinary. But it's got nothing to do with the sunspot cycle.
Anybody else got any questions from the floor or from those joining in via the net? Okay, well, I'd like to take the opportunity to thank Roger enormously for his talk this evening. It was recorded. We will endeavour to get that up on our YouTube page as well, with Roger's permission. So I'm sure it's one of those things that we'll keep looking back over and over again until we get the picture clear.
Is it available in hard copy also?
Available in hard. That's a very bad man. Okay, so we'll take the opportunity to thank Roger in the traditional way. Thanks, Roger.
All right, thank you very much for that.
You had a question?
An observation.
Go
I'm not a ham very active for a long time. I've done satellite TV work, and I'm from South Africa. And I used to watch a satellite over in geosynchronous orbit over Singapore.
on. Yeah,
It's a Russian satellite, one of the first ones they put up as soon as they realized they could cover all 11 time zones of Russia with, I think it was called E-crane. And one Saturday morning at home, I went to a cup of tea and I went and sat and switched my system on. No satellite, no signal, nothing, gone. Nothing, I could see nothing of it. And I had a solid satellite signal on my seat. So I had a look at the antenna. I thought the wire had fallen off the pickup or something, no? So the antenna is pointing in the right direction and it's in one piece. Now the satellite is FM modulation.
yeah.
So I took my special homemade receiver off, antenna signal into the normal terrestrial transmitter. I had 12 volts coming out to power the preamp, 40 dB gain preamp.
Yep.
And a big dish of about 26 or 28 dBs gain.
Uh-huh.
And I got with the normal ground TV receiver, I've got a ground transmitter, bang, from 300 kilometers away. That's the African ground transmitter, television transmitter, bell, color, sound, everything. Sitting there. Normally it would be very grainy with just enough to get color in modulation, bell color demodulation. And it was coming in there like a rock. Bang! You look on the screen, you don't see any little speckles, colored noise, nothing, nothing.
5 and 9,
And
P5, yes.
so I looked at this, I thought, heck, this is unusual. It must have been some sort of ionization.
What frequency are we talking about?
This is the thing, don't give up on 432 megahertz. UHF, 720.
It's extraordinary.
And I sat there and I said, never mind, my teacup was empty. Watching. And I could see the speckles of noise coming in and back. And I thought, oh, here we go. This only happened once. I never saw it the second time. And it was gone.
It wasn't Trippo, wasn't Chemistry.
That figure, I don't know what caused it.
Oh, yeah, well, Trippo would.
It's Trippo.
Up on 720.
Yeah,
Oh, yeah, we've done it on 3.4 gigs.
Yeah.
Yeah, 2,500 kilometers.
Quickly put my other antenna up and FM receiver. And the Russian TV was back.
Yeah.
Interesting. Just like that. So the ionization stops signals from getting up from the satellites to us. The attenuation increased dramatically.
Yeah, maybe. Hard to say. Depends on
how the propagation rate could be. But
I never saw it again. But if you want to go on 430 megahertz,
yeah, so you've got to be sort of like on the ball at the time.
the point I want to make is if you've got a high gain antenna, very directional, and I was pointed 8.5 degrees up.
Right.
I could just get the satellite above the horizon from 7 over Singapore, 8.5. So if you want to try it, have a high gain antenna.
On 432,
That's easy.
yes, that's straightforward.
Make a parabola. It is easy.
Sometimes hard to fit in place.
Well, it stood up high over the
All right, well, thanks for that, that story. Okay, just a few little bits and pieces from the club. The May meeting, it's on April the 26th. I'm actually going to be away, so Doug's going to organise that meeting for us. And we also have a microwave activity day next month in April on the 23rd. Did you want to say something, Doug?
No, you said the May meeting.
April.
Yeah,
April.
April and May. that sound the
April
same.
and 20 is the 26th. The May meeting will be our AGM, of course. That's on the 24th of May. And we'll be having elections for the position holders in the group. And as you know, as we've asked before, Peter's standing down as treasurer next year. So we need somebody to consider standing up for that position for next year. Couple of other things to know. The Redfest convention up at Redcliffe, that's on April the 1st. So that's only, what, a week away now. So that's on coming up soon. We had a microwave activity day last weekend that coincided with the John Moyle Field Day. I'm not going to say any more about that. I'll ask others to just indicate shortly what they did. So there were quite a few people out entering or at least participating in the VHF and microwave side of the John Moyle. Beacons, a little bit of news about the beacon system. Currently the RBB, that's the 70 centimeters up to 24 gigs. That's all working except the 3.4 gig PA seems to have stopped. And we left that on deliberately over the John Moyle weekend so that everybody could use that for as a signal source. But hopefully we'll have that unit removed and the 3.4 system looking to see what the problem is with that very shortly.
Can I just add in
yes.
there that Graham, the 2SRC, was just occasionally in, occasionally out, very weekly copying 5.7 gig beacon.
Okay, well, that's good to know.
Nearly the whole weekend, just sometimes there, sometimes not.
Okay, RTT, that's the 6 and 2 meter digital.
Need to run more power than 5.7 gigs.
It would be good. The 2 meter, 6 meter beacon, a VK4 RTT, that survived its long soak test at Doug's QTH. We had problems with the phase lock loop systems and the ZL beacon controller. That's all been rebuilt and re-established into a nice new enclosure, courtesy of Peter. And Doug ran it at his QTH for several weeks, and it ran faultlessly, basically. So that's come out of Doug's QTH now and is going back into its own rack with its own PAs. We went up and did some work up at Mount Cootha, where its final home would be. There's a new rack installed up there. So the next stage will be to give the beacon its controller plus some PAs, and it'll have another soak test and see how it goes. But we may hopefully have that on the air on a semi-permanent basis before too long, before it goes back up to its own location. I'm going to throw it over to the floor now, and people can just describe what they did in the John Moyle Field. It was pretty successful. I was out, and I was pretty happy with some of the results we got. Doug, do you want to say anything about what you did?
Well, I'm with Andre here. We went up to have some fun just on Mount Cootha for a few hours on Sunday morning. And easy contacts on, well, actually, when we first started, it was struggling on all bands to get down to VK2SRC, just on 300 kilometers away. But as the morning went on, things stabilized and people came fairly good on 1296 and 2.4 and 3.4. And we tried 5.7, and I'm hearing him about strength 6 or something, but he's not hearing me at all. Something troubleshooting after I got home. A 10-pin control cable connector was not even connected, so it was stopping the transmitter going. So
It's all right, Doug. We working on 5.7.
yeah, I heard that. That's good.
Do you want to talk about what was done on the Saturday?
We just went up there and we had 3 stations set up and we worked on 5.7, 2.4, 3.4. Yeah, I just used a 600 mil dish, 5.7, 8 watts. Kevin, that is, and we had the 80 watt 2.4 and a 1.8 meter dish up there. That got through all right.
Yeah.
So, yeah, all worked well.
What
Feeder
sort
was
of feed
there.
are you using on 2.4?
Sorry?
What sort of feed are you using on the dish?
RFN design, circular feed. Yeah, just a ring
Oh, I see.
ring
Yes,
feed.
I know.
It's a dual band one's 1296 and 2.4.
I have a triple one, which I bought from Doug,
Mm.
which I've subsequently divested when I moved out of Sydney.
Yeah, I've got one that goes from 1296 to 10 gigs also.
Pete had his 5.7 gig system with the big dish as well. And you certainly copied the SRC because he's running what, 2 watts down there, wasn't he?
No, 5.
5. Okay.
Oh, QRL.
So how big is your dish? So we had a 1.2. I had the 1 meter dish, and Cole had the 600 mil dish. I had a multi-band feed on mine. You had a single band feed, and Cole's got a single band feed. And the far and away the outstanding performer was actually the 600 mil dish with a short length of feeder. I mean, it's just a lesson that we should all know that in fact you worked in both ways with ease, and I struggled.
No, the only reason was yeah, I said when I got there, where are they? And you said there. So I drove further down. You lot were parked looking at trees.
Yeah.
The greenery was blocking the view.
I don't think my dish is on.
I'll have that tripod.
But that's the first contact that the SRC group have ever had on that band. They've never worked anybody before, so their debutante contact was to 300 and something kilometers, which is certainly my best DX on that band, and yours too, and certainly theirs. So and that's the system that Doug built and sent down to them. That's the first time they've ever activated that band and had a contact. So yeah, we had a fairly successful weekend.
Yeah, it was good.
I was copying 5x6, capital 6 on the meter.
Mm.
And I was that's not where you were on that, Cooper.
You're further up.
I'm beaming through gaps in the tree. We were, and but I both optimized the actuator dish thing, you know, the azimuth and elevation able to be adjusted like that, and a big improvement to get the elevation correct.
Yeah, well, it's the same on 2.4 because I can do ASL on 2.4 with the 1.8 meter. And it was the same because thank God John was there. He jury rigged up some electric connections so we could adjust it.
There's forceps.
Yes, yeah, it was quite interesting, but it worked. And like on 2.4, they were like, you know, 2 or 3 on the S meter and then up to S7.
This guy's amazing. He had the Paul forgot his control
I
box.
forgot the control box should be
There's
ASL.
2 of these 4-pin Udilux connectors hanging out with exposed spade lugs. So John gets 2 pairs of forceps and puts it onto the plus and minus, and then gets some jumper pads and flips onto that to get the 12 volts to the motor to move that left and right.
Yeah, once we got a point in the right direction. And the 5.7 was just one of those surplus dishes we brought home. Kevin brought 2 of them back from Tasmania. And we shipped up here. They're just old commercial links. They work like a treat.
Push the feed for the part of mine. So didn't have much luck with mine.
Yeah, they're just like a bit of wave guide, feed in it, and at the end.
So one other thing that
There we go.
Yeah, there you go.
Good. One other thing that happened on the field day was because it's to John Moyle, I took along the 40 meter and 20 meter whip for HF, and I didn't work a few. I wasn't John Richard, but Andre, using his own call sign, had his very first contact on any band.
Well done.
Yeah, well
on 20 meters it was.
Yeah, we had a bit of trouble with the 80 metre width wasn't working. Did you get to the point?
No.
Well, I like the John Moore field day. So when I had, the ink was barely dry on my licence. And so I organised to, being a limited licence, I got a couple of 6 to 2 metre rigs, only running a few watts, etc. I already had some antennas. I didn't have a driver's licence. I got my father to drive me up to a nature park on the hill at Mount Albert, and spent the weekend flattening batteries, and entered a log, and lo and behold, won the VK3 set.
John Moyle.
You never know.
You got to be in it to win it.
This is Cole's expanding umbrella dish. Press the button on the back and it goes doink, 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 and comes out. It's the most amazing thing you've ever seen.
You've got to get a video of that online.
We've actually got one somewhere.
Yeah.
We'll put it up on one of our.
It's handy. No, but the 5.7, I was really happy with that 600 mil dish.
That's the white one there. Isn't it? That's fine.
Yeah, and then that tripod there was the other one that the 10 gig system sat on until it decided to fall off.
Incidentally, from other members, none of who are here at the moment, you recall about 6 months ago, we actually Colin and I drove up to Rockhampton and worked back to aircraft scatter on 3.4 gigs and exceeded the state record. Frank, who lives in Zilsey, and Trevor are now doing that almost on a daily basis.
They did it again
aircraft.
yesterday morning.
Oh, bloody
So
hell.
they've been doing it on 1296 for quite some time, and they're now, because they're doing it every day,
So that's just proper stuff.
just Troppo. So they're getting a 50% hit rate and doing it every day.
Yeah.
Really?
Trevor couldn't hear Frank yesterday, but Frank could hear Trevor. But Trevor's running a bit more power than Frank. So yeah, no, they do it almost daily now. They found the sweet spot.
I built the same PA up that Trevor's built. Makes 150 watts on 3.4 gigs, and the guys at SRC were getting true 5 and 7, 5 and 8 signals from me. And when I've tried up to work Frank from Mount Cootha the last time we were out on digital, he copied me every single transmission period and decoded me, and I heard nothing from him whatsoever. So a little bit of power makes a huge difference up there.
Could I just comment on that path from anywhere around southeast Queensland to VK2 SRC? He's on a very high hill down near Glen Innes, New South Wales. There's the nightcap range and the coastal McPherson ranges and things like that. Definitely higher than obstructing the line of sight path to do path profiles on it. But the propagation there, like
Just need people to be at the other end, don't you?
Rod, VK4VU, he estimates 500 milliwatts of output of RF at the dish. He was working VK2 SRC
Wow.
on 3.4.
It's amazing, isn't it?
Yeah.
Just got to be there, go through the line in the water, catch the fish.
Yeah,
No, I was their first contact on 3.4
What I'm
from
getting
home
at,
with 2 watts at the bottom with 20 meters of colour.
I reckon there must be not just trees and everything, there must be a good knife edge or something like that that's between. Something's working.
Well, we have talked about if we're not going to do a major entry from up here, going down, taking 10 gigs down to Vista Point when they're there, and trying that path back up on 10 gigs or even higher. And that may still happen. I think that's it. It would be a very interesting path to try next band up. We've done it up to 5.7 now. We know it's going to work. There's no it's going to work.
Oh, I'm sure it's going to work. In fact, normally for 24 gigs, you think if it's not line of sight, it's not on. That's what you normally think. But if it's scattering over this path on up to 10 gigs quite well, I reckon there's something got to be, give it a try.
You got to try.
An early start.
I got a question for Doug, if I may. Doug, do you think Mount Cravat Lookout's a bit overgrown?
Yes,
Yeah, because my dishes are sort of at sort of waist height or chest height, and we couldn't get down to SRC, but everything we had up in the air, 1296 onwards, we were doing quite well. But anything that, as I said, around about weight or shoulder height, waist height, it just we weren't doing any good at all.
yeah, totally.
Except for Kevin and AFL, sorry, and Cole on the other bands. But I'm just interested because I thought, well, we're going to have to lift those particular dishes further up somehow and work them up there. But anyway, just a confirmation for that. Thank you very much.
And thanks to you too for coming up, John. You're putting out a good signal on all the bands that we worked you on.
Cole might be interested. Thank you for that.
And lost you, but
no, don't worry about that. There was 5 of us up there. We were doing the John Moyle, and we decided to bring 10 up to 10 gig. My 5.8 still in the doctors, but anyway, one of these days. But Cole, I was using that little I can't remember, Spanish 2.4 gig.
It's a little 2.4 gig system.
Yeah, that's got what's left of 8 watts out of a Wi-Fi 2.4 gig amplifier. But you guys were screaming in. I guess you weren't that far away, but it was a bit unfortunate we couldn't get any further, either north or south. But anyway, it was a great day. We all had a good time. I know that. And
we've still got one of those little transverters lying around. They got that 51 meg IF on.
Yeah. Yeah, that's why I like it, because it doesn't get interfered with by 2 or 70.
No, it's good like that.
okay, well, on that point, I'll thank everybody for joining in tonight. It's been very interesting. It's good to see so many on. Don't forget, we've got that next microwave activity day. That's the next opportunity to get on the hilltops, April the 23rd, Sunday. And the next meeting here will be on April the 26th. So thanks everybody for joining in. Good night, and 73.